Hello everyone, here we are again back to chapter 3. In this section we're going to learn about the chemical equations, how to write the equations and how to balance the equation. Okay. A chemical equation uses formulas to express the identities and quantities of substances involved in physical or chemical change. Now here we have a calculation. Here we have a reaction where we have 1 mole of hydrogen with 1 mole of fluorine giving us 2 moles of hydrogen fluoride. Now 1 mole of hydrogen, if you look at the molar mass of hydrogen, 2 moles, that would be 2.016 grams, and this is 1 mole. So when we write the equation like that, it represents in terms of moles 1 mole, but in terms of grams 2.016 grams hydrogen. 1 mole fluorine represents 38 grams because 1 fluorine is 19 grams. Okay. And similarly, if you have 2 moles hydrogen fluoride, 1 mole of hydrogen fluoride is 20 because hydrogen 1, fluorine 19. So 20 times 2, 40 grams. And this is the molecular representation of the hydrogen, fluorine and 2 moles of hydrogen fluoride. The same as atomic mass unit, 2.016 atomic mass unit, 38 atomic mass unit and 40 AMU. And this is the equation in the symbol form: hydrogen gas, fluorine gas, giving you 2 hydrogen fluoride gaseous molecules. Okay. If 1 mole divided by Avogadro's number will give you in terms of molecules. So we can find all that information in a equation, balanced equation. Features of chemical equations. The equation must be balanced. The same number and type of each atom must appear on both sides. Now here we have an example: magnesium with oxygen giving you magnesium oxide. Magnesium is the reactant plus oxygen yield arrow magnesium oxide. Now this reaction is not balanced, so we need to balance it. Okay. How do we balance it? Okay, let's see what to do in order to balance. So there are 2 oxygens with O2. So what you need to do is, you're not going to put your 2 right next to oxygen. That will make a different formula. So we want to make sure your formula is correct and you don't mess with the formula. So you don't do that. So instead you're going to balance it. You take the oxygen 2 and then you always put it at the front as a coefficient. So 2 oxygen. Now it made 2 magnesium. Now how do we balance the magnesium then 2? So we're not going to do anything like that to make it Mg2 because it doesn't exist. So what you need to do is, you need to put the 2 at the front. 2 magnesium. Now there are 2 magnesium and 1 oxygen giving you 2 magnesium oxide. 2 magnesium on the reactant side, 2 magnesium on the product, 1 oxygen O2, and there are 2 oxygen in the product side. That's the balance equation. Translating the statement, we first translate the chemical statement into a skeleton equation. And then we balance the atoms. We match the numbers of each type of atom on the left and the right of the yield arrow. And then we adjust the coefficients. In most cases, the smallest whole number coefficients are preferred. And then we're going to go and check. After balancing and adjusting the coefficients, we always check that the equation is balanced. And then we specify the states of matter. The states of matters are going to be solid, liquid, gas. And if you are doing a reaction in a water medium, we put AQ to represent aqueous. The final equation also indicates the physical state of each substance or whether it is dissolved in water. Now these are the three level view of the magnesium and oxygen, giving us magnesium oxide. In the macroscopic view is what we perceive and what we see. So this is a magnesium ribbon. You burn it in the air, magnesium oxide is formed. In the atomic scale view, magnesium is a metal. Magnesium atoms are close to each other. Oxygen is found in the air and it is in the form of O2 molecule. It's a gas. And then once magnesium oxide formed, it is MgO. In this one, magnesium is +2 charge and oxygen is -2 charge. MgO, solid. So both of magnesium is a solid, oxygen is a gas, and then magnesium oxide is a solid. And this is the balanced equation: 2 magnesium with 1 oxygen, giving us 2 magnesium oxide. Okay. Within the cylinders of a car engine, the hydrocarbon octane C8H18, one of many components of gasoline, mixed with oxygen from the air and burns to form carbon dioxide and water. Write a balanced equation for this reaction. So, again, if you are burning anything, so this is octane, the formula given C8H18. Burning means you burn with oxygen. Always a hydrocarbon with oxygen produces carbon dioxide and water as the products. Even if it is not given to you, you should know a burning or combustion, a hydrocarbon mean burning with oxygen, giving carbon dioxide and water. Now we're going to balance this. So there are 8 carbons. So we need to have 8 carbons on the other side. Right now we have 1. So you put 8 at the front. And then hydrogen, there are 18. So here you have only 1 hydrogen. And you don't put 18 here. If you put 18 times 2 will make it 36. So instead you put 9. So that will make 9 times 2, 18. Now by doing that, what did we do for the oxygen? How many oxygen do we have on this side? So there are 8 carbon dioxide, 8 CO2. This 8 belongs to carbon as well as oxygen. So there are 2 oxygen already. So 2 times 8 make it 16 oxygen. Right? So there are 16 oxygen on carbon dioxide. And for water, there are 9 oxygen. So 16 plus 9, that is going to be 25 oxygen on the right side. Okay. So here we have only 1 oxygen. So at the beginning you can see we need 25 oxygen. So you can put 25 over 2. So 25 over 2 times 2 oxygen. So this 2 and this 2 get cancelled. Then we have 25 oxygen. You can start it as a fraction to begin with. But normally in a balanced equation, we try not to keep fractions like this. So if you want to make it whole numbers, what you're going to do is you're going to multiply this whole equation by 2. So by doing that, you receive this equation where 2 C8H18. So 2 times 25 over 2 is 25 oxygen. And then 2 times 8, 16 carbon dioxide. 2 times 9, 18 water. Okay. So that is going to be the balanced equation. 2. So the second one is the same thing, or the fourth equation, this one, and the third one, they are the same. And then once you get the atoms balanced, then you can specify the state of matter. Octane, it's a liquid, which is the gas that you put into your car. And oxygen comes in terms of gas. And carbon dioxide is gas. And then the water again, water vapor. Okay. Carbon dioxide and water vapor. So you specify with the states of each reactant and the product. So that is the balanced equation. Okay. Now we can visualize the reaction we just now did with the molecular scene. Now there were 2 octane molecule, C8H18. So these black atoms are your carbons, and then the blue ones are your hydrogen. So there are 2 molecules of octane, and there are 25 oxygen molecules. You see O2. There are 25 O2 molecules going to form 16 carbon dioxide. So carbon from the octane, oxygen, red oxygen from the oxygen combine to form carbon dioxide. 1 carbon, 2 oxygen, and there are 16 of carbon dioxide. And then the water, H2O, hydrogen from octane and oxygen from O2 form H2O, 18 H2O. Now all the hydrogens now end up being on water molecules. All the carbons will end up in carbon dioxide, and oxygen will divide into your carbon dioxide and water according to the balanced equation. All being used up, nothing left in a balanced equation. Okay. All being used up of the reactants, and now they are in the form of products. In a balanced equation, you see we use the coefficients, and they are the number of moles. Okay, so in a balanced equation, the amounts, which is the number of moles of substances, are stoichiometrically equivalent to each other, which means that a specific amount of one substance is formed from, produces, or react with a specific amount of the other. The quantitative relationships are expressed as stoichiometrically equivalent molar ratios that we use as conversion factors to calculate the amounts. Okay, now let's look at that concept in detail with this example. Information contained in a balanced equation. So we have reactants as C3H8 plus 5 oxygen, giving us 3 carbon dioxide and 4 water molecules. Okay, so these are your reactants and these are the products, and then we can balance it similar to how we balance the octane molecule. You see there are C3H8 and oxygen. Let's consider it like that, just oxygen, O2. Okay, let me show you how to balance it over here. So let's say you have C3H8 plus oxygen giving us carbon dioxide and water. Now, this is the unbalanced reaction. Let's see how we can balance and get these molar ratios. There are 3 carbons, so we can balance it by adding 3 next to carbon. And there are 4 hydrogens, so we can put 4 here. That will make it 2 times 4, 8. Now, carbon and hydrogens are balanced. How many oxygens on the right side? On carbon dioxide, 2 times 3 is 6 oxygen. So we have 6 oxygen here. And then 4 times oxygen, 4. So 4 and 6 will make it 10 oxygen on the right side. So we need 10 oxygen on the left. So you can put 5 there, 5 times 2, 10. So that is the balanced equation that you see here. Okay. C3H8 plus 5 oxygen, 3 carbon dioxide, 4 water. That's the balanced equation. Now in terms of molecules, 1 molecule of C3H8, in other words, C3H8 is propane, okay, with 5 molecules of oxygen, give you 3 molecules of carbon dioxide, 4 molecules of water. And remember that the stoichiometric ratio that we talk about, so these are the stoichiometric ratios. Okay, 1 mole propane plus 5 moles oxygen stoichiometrically giving 3 moles carbon dioxide and 4 moles water. And then in terms of mass, atomic mass unit, C3H8, there are 3 carbons, 3 times 12, 36, plus 8 hydrogens, 8 will make it 44 AMU, which is same as grams. And then 5 moles oxygen, O2, 16 times 2, 32 times 5 is 160. Okay, that is the mass of oxygen. And then 3 moles carbon dioxide, each carbon dioxide is 44 because carbon 12, 2 oxygens 32, 44 times 3, 132. AMU similar to grams. Carbon dioxide. 4 moles water, water molecule is 18 times 4, 72 atomic mass unit or grams. So these ratios excuse me, remains the same in this stoichiometrically equivalent reaction. Okay, and then if you look at the total mass, 204.09, 204.09 reactants are same as the mass. Again, it obeys the mass law as well. Okay, so this is one propane molecule react with 5 moles of oxygen, giving us 3 moles of carbon dioxide and 4 moles of water molecules. Now tell me, if you start with 2 moles, so this is 1 mole of propane giving you 3 moles of carbon dioxide. What about if you start with 2 moles of propane? How many carbon dioxide molecules would you make? Remember, 1 will give you 3. If you start with 2 moles, ratio is 1 to 3, then 2 to 6. What about water molecules? It would be 8. How many of oxygen molecules will react with 2 molecules of propane? If 1 to 5, this would be 2 to 10. Do you see that? That is what means they are stoichiometrically related. If something changes the amount, others also going to change accordingly. Okay? Okay. Now let's look at this concept with a problem. Copper is obtained from copper 1 sulfide by roasting it in the presence of oxygen gas to form powdered copper 1 oxide and gaseous sulfur dioxide. How many moles of oxygen are required to roast 10 moles of copper 1 sulfide? Okay, first we need to know how to write the balanced equation with the proper formulas. Now I taught you how to do the formulas. Let's look at that. Copper is obtained from copper 1 sulfide by roasting it in the presence of oxygen gas to form powdered copper 1 oxide and gaseous sulfur dioxide. Now in this case, what are our reactants? What are the reactants? Reactants are going to be copper 1 sulfide and oxygen gas. What are the products? Products are going to be powdered copper 1 oxide and sulfur dioxide. So we need to draw the reactants and the products with the proper formulas. Copper 1 sulfide, meaning copper is +1 charge. And sulfur, what's the charge of sulfur? Normally sulfur is in group 6, it makes -2. So copper 1 sulfide is going to be then Cu2S. So your 2 goes right here and 1 goes there, Cu2S. And then we have oxygen. Normally oxygen exists in nature as a diatomic molecule, so you have to write it as O2. And the products, powdered copper 1 oxide. Copper 1 again, copper 1 plus charge, oxide again in group 6, common ion it forms is -2. So what's going to be the formula for copper 1 oxide? Remember, we have to say copper 1 because copper can be 1 or 2 transition element. And they have to write in parentheses what is their charge. So copper 1 oxide then would be, you crisscross the values, that would be Cu2O plus gaseous sulfur dioxide. Now sulfur dioxide, How do you write sulfur dioxide? That is going to be SO2, which is a covalent compound. Copper 1 sulfide and copper 1 oxide are ionic, so we don't have to use any prefixes. But sulfur dioxide is a non-metal, a covalent compound, so we use SO2, sulfur dioxide. So now that is our equation with the proper reactants and the products. We need to balance it now. It's not balanced, is it? It is. Looks like it is. So there are 2 copper, 2 copper. Oh, it's not balanced. You see, copper is balanced. There are 2 copper, 2 copper. 1 sulfur, 1 sulfur. What about oxygen? There are 2 oxygens here, and on the right side you have 1 oxygen here and 2. So there are 3 oxygens on the other side. So how do we balance it? If it comes as an odd number, remember we can do it like this to begin with, 3 over 2. 3 over 2 make it 3 oxygen. But normally we don't keep it as a fraction. So what we're going to do is, to get rid of the fraction, you multiply the whole thing by 2. So that will give you 2 copper sulfide plus. So 2 times 3 over 2, 3 oxygen. And then 2 Cu2O plus 2 SO2. That's going to be our balanced equation. Also we can specify copper sulfide is going to be solid. So this is going to be a solid, and this is a gas, and this is a solid, and SO2 is a gas. So that is the balanced equation with the proper states right here. This is what we just did. Okay. Now what's the question? Let's go back. Copper is obtained from copper 1 sulfide. Okay, it's asking how many moles of oxygen are required to roast 10 mole of copper 1 sulfide. So copper 1 sulfide, 10 moles. Copper 1 sulfide, 10 moles. It is asking how many moles of oxygen. You put a question mark, what's been asked, and you write down what's given. Correct? So read here again. It's asking how many moles of oxygen are required to roast 10 moles of copper 1 sulfide. So you identify what are the 2 things that you are looking at. Copper 1 sulfide and oxygen. Copper 1 sulfide and oxygen 10 moles. And then we will see how we're going to set this up. Okay, we want to find out moles oxygen is what we want. We want moles oxygen. That is going to be on the left side. And on the right side, we always start with what is given. We are given 10 moles copper sulfide. Okay. Then what you're going to do, you use the molar ratio between copper sulfide and oxygen, because these 2 are the one that we are interested. At this point, we're not going to worry about the copper oxide or the sulfur dioxide, and we use the molar ratio between copper sulfide and oxygen. Since we started with copper sulfide, it needs to balance, or it needs to cancel with the copper sulfide moles. So the balance equation tells us 2 moles copper sulfide react with 3 moles oxygen. So you put that here, 2 mole copper sulfide, and then you put 3 mole oxygen in your numerator. So that is the molecular ratio, that's the molar ratio you get from your balanced equation. So mole copper sulfide cancel, mole copper sulfide cancel, and then you just do the math part. 10 times 3, 30 over 2, 15. 15 moles oxygen. Okay. That is the number of moles of oxygen needed to react with 10 moles of copper sulfide. Ratio 2 to 3. So we use that ratio as a conversion factor. And then the next one. During the process of the same question, we're going to be working the problem in different ways to show you how we can get different either moles or grams. Okay. During the process of roasting copper 1 sulfide, how many grams of sulfur dioxide form when 10 moles of copper 1 sulfide reacts? Okay. Now it's asking how many grams of sulfur dioxide form when 10 mole of copper 1 sulfide reacts. Now this is your sulfur dioxide. We want to find it in grams. When 10 mole of copper 1 sulfide, 10 moles is given. We want gram sulfur dioxide. Now in this case, we are going to look at the molar ratios of copper sulfide and sulfur dioxide, which is given to us from the balanced equation as 2 to 2. That's what we're going to be doing. Now we want gram sulfur dioxide. We always start with what's given. What is given to us? 10 moles. 10 mole copper sulfide. And then you're going to convert, then you're going to use the molar ratio to find out the number of moles of sulfur dioxide. Okay. And then the molar ratio would be from the balanced equation 2 moles Cu2s give you 2 moles SO2. Basically 2 and 2 can get cancelled, 10 moles SO2. But we don't want the moles, so that these moles to moles cancel. Right now what we have made is the number of moles of sulfur dioxide, but we want it in grams. So how do you convert moles to grams? We use the molar mass. So 1 mole sulfur dioxide is the molar mass of sulfur dioxide. Sulfur is 32 and 2 oxygens 32 is about 64 grams, right? 64 grams. Write the proper significant figures up to 4 significant figures. Okay, when you do your actual calculation, I don't have space there. So 64 times 10, 640 grams SO2. So we have the units what we want, grams sulfur dioxide. You see, you start with what's given and then you find out what 2 things you are looking at and use the stoichiometric molar ratio from the balanced equation. And then if it is asking grams, you convert it to grams using the molar mass. So the molar mass is 1 mole sulfur dioxide is 64 grams. So 640 grams. Okay. Or 641 if you use the proper values from your periodic table. The same problem continues. Now it is asking the same process during the roasting of copper sulfide, copper 1 sulfide, how many kilograms of oxygen are required to form 2.86 kilogram of copper 1 oxide. Now it's asking how many kilograms of oxygen required to form 2.86 kilogram of copper 1 oxide. So now we are looking at copper 1 oxide and oxygen. So these are the 2 things that we're going to look at. We are given 2.86 kilogram copper 1 oxide. 2.86 kilogram. And we need to find out how many kilograms of oxygen. So this one we need to find in kilograms. Okay, we have more space there. How do we do this one? We start with always what's given to us, right? So we are given 2.86. That's what we start with. So you start with 2.86 kilogram copper oxide. And we can convert this into grams. How do you convert it to grams? Since we are asked to convert it to kilograms of oxygen, we don't need to convert it to grams. We can do it with or without. I'll go ahead and convert it. Okay, let me do this. So 2.86 kilograms, if you convert it to grams, there would be 1 kilogram is 10 to the power 3 grams. Okay, so that will make it 2.86 into 10 to the power 3 grams. That is copper oxide, Cu2O. Now, we are going to relate to oxygen to copper oxide using the molar ratio 3:2. Right now, what we are given is the grams. So, in order to use the molar ratio, we first need to convert copper 1 oxide grams into moles. How do you convert grams to moles? Using the molar mass of copper 1 oxide. So, 1 mole, it's going to be in your numerator. 1 mole copper oxide is the molar mass of copper oxide. So what is the molar mass of copper oxide? That is 143.10. 143.10. You can calculate the molar mass of copper oxide. So first step is converting grams to moles of copper oxide. And then you use the molar ratio, which is copper oxide, 2 moles copper oxide will react with 3 moles oxygen. So 2 moles copper oxide goes to your denominator, because we start copper oxide in the previous one right here as your numerator. So 2 moles copper oxide goes to your denominator, and then the ratio would be 3 moles oxygen. Okay. And then we can continue further, or if you want you can stop and find out the number of moles. So since I'm running out of space here, I'll go ahead and calculate the amount. So 2.86 times 3 over 143.10 will give us the number of moles of oxygen. That's going to be, we do the calculation, 2.86 times 3 over 143.1 over 2, 29.97. 29.97. That will give us the number of moles of oxygen. Okay, 29.97. That's moles oxygen. Gram copper oxide, gram copper oxide. So moles oxygen, 29.97. So we can continue here. 29.97 moles oxygen. We found the number of moles of oxygen. And then the next step is converting moles oxygen to grams oxygen. Using the molar mass of oxygen, 1 mole oxygen, see it is O2, it's going to be 32 grams oxygen. And then we need to convert it to kilograms. 1000 gram is 1 kilogram. So this number, 32 over 1000, 0.959 kilograms. So that will give you 0.959 0.59 kilograms of oxygen. Okay, that's how you find the mass in terms of kilograms. Okay, so we can stop this section here, and then we'll talk about the reactions in sequence the next session.